Well, good afternoon and or good morning still here in Mountain Time or out on the West Coast. Welcome to the ASA October Brown Bagger. We have Dr. Annabelle Pratt with us today. Annabelle, welcome. Glad to see you with us. And we're looking forward to first hearing her talk from the 2017 annual meeting in Golden, Colorado. And some of you will have heard that talk. I know I've am looking forward to hearing it again and going back over that territory. And then we're also going to have some time at the end for some question and answer. The way that we'll work today is we'll begin with Annabelle's talk. Then she has a few minutes in which she's going to update us. Much has happened in the area of renewable energy across the last few years. It's a dynamic field. Much is happening, as we all know. It's in the news regularly. Just so we know, Annabelle has another meeting. There's a relatively hard stop at the top of the hour. We might be able to sneak over a few seconds or a few minutes into that, but then you'll put her late to a government meeting, and we don't want to do that if we don't have to. So we'll see how it wraps up. But if we're in full flight on a really interesting question, we do have just a little bit of wiggle room there at the end today. So with that, Mark, I'm going to ask you to cue up Annabelle's talk from the 2017 Golden Meeting on Renewable Energy.
So Annabelle is here because she's a personal friend of Kenturian and myself, and she's been active in ASA for a good number of years. I'll tell you a little bit about her background. She received her bachelor's and master's degrees in electrical and electronic engineering from the University of Stellenbosch. I think I got pretty close to it. South Africa. And her PhD in electrical engineering from Oregon State University. She's currently a principal engineer with the National Renewable Energy Lab. And prior to joining NREL, she was a senior power research engineer with Intel Labs. Previously, she was with Advanced Energy Industries, where she developed power supplies for the semiconductor manufacturing and architectural glass coating industries. Her research interests include autonomous energy management of flexible loads in buildings in order to increase the penetration of renewable energy resources. So, let's give a warm welcome to Annabelle Pratt.
Well, good evening. Thank you very much, Lynn, for the introduction. And I attended my first annual meeting of the ASA in 2003 here in Colorado at the Colorado Christian University. And at the time, Jennifer Wiseman gave a plenary talk and had these beautiful photographs of space. And unfortunately, I don't have anything quite as dramatic this evening. The best I can do is a picture from space of the Earth. This is a composite picture of Earth at night, and it shows quite vividly the tremendous impact that electrification has had in our world. And as Lynn mentioned, I am from South Africa, the southernmost country in the continent of Africa. And this evening, I will give just a very brief history of my involvement with ASA. And then I will introduce some basic concepts of the traditional grid as it stands today before launching into a discussion of what is going on in the field of grid modernization. So Len, you did a great job with Stellenbosch, a beautiful city, one of the oldest cities in South Africa, where I completed my bachelor's and master's degrees. And at Oregon State is the time that I joined ASA. I joined the Graduate Christian Fellowship when I arrived at Oregon State. And one day, a professor from the faculty Christian group came to our meeting and talked about ASA, handed out some flyers. He was really interested, signed up, and so have been receiving the journal perspectives for 20-some years. And then when I moved from my first job in Fort Collins, got involved with the Rocky Mountain chapter and worked with Ken, Cheryl, and many others, and attended that first annual meeting. And then we moved back to Oregon. There's a theme here. and joined the Oregon area chapter there. And when I moved back 3.5 years ago to join NREL, contacted Ken and said I'm back in the state and have been again involved with ASA. So it's been a tremendous part of my life, and the sometimes struggle and other times just learning about that interface of faith and science. So the National Renewable Energy Lab, I did want to say just a few words. I'm so happy that many of you were able to attend the tour this morning. Many have, I was at the workshop that Brent Nelson, a colleague, gave this afternoon, and many said that they really enjoyed it. So we're delighted that some of you visited. The Department of Energy has 12 national laboratories, and NREL is one of them. It is the only one dedicated to renewable energy and energy efficiency research and development. So it's quite a broad range of work that the Department of Energy oversees. So it was founded as the Solar Energy Research Institute in 1977, a time when there were early stage solar panels on the roof of the White House. And in 1991, it attained national laboratory status. And that's where I have the pleasure of spending my work time right now. So in the United States, we are fortunate to have near universal access to electricity. And much of that, especially in the rural areas, is thanks to the expansion, the rural electrification programs during and after the Great Depression. But over the past 10, 15 years, outages have been increasing. So yes, we have a very reliable grid, but we are losing some of the performance that we have become accustomed to over the past years. And a couple of reasons. One of them is that our infrastructure is aging. One statistic is that more than 70% of our transmission lines and transformers are more than 25 years old. So we have older infrastructure that needs a replacement, and that provides an opportunity for upgrade. And the other aspect that I'll talk more about tonight is as we bring new technologies into the grid that was not originally designed for those type of technologies, we need to rethink and re-engineer the grid to be able to absorb those technologies more efficiently and successfully. So the grid, I speak of the grid, but in North America, it's actually 3 grids. It is the world's largest machine. It is amazing, just the geographical scope and the amount of energy that is running synchronously in these 3 areas in the United States at any given point in time. So we have Texas being separate, and also Quebec. And then the eastern and western interconnects. And so at any given point in time, these systems, everywhere across that huge landmass, you run at 60 hertz at the same phase angle in your sine wave. So the grid, so synchronism is one of its main jobs, and the other is to supply the appropriate voltage and keep that stable throughout throughout load changes, weather changes, etc. So just a 101 on the traditional electric power system. So here we're going left to right. So we have a grid that is built around central power stations. And mostly that is coal and natural gas in the United States. So that generates the power. It is transmitted through transmission lines. These are the big lines that you drive down the interstate. You have very tall towers, big spacing between lines. And that voltage is then stepped down at first transmission substation. And many industrial customers that have very high power requirements use voltage at higher levels, 69 kV, 34 kV. And then it is stepped down at a distribution substation, and that's more familiar to us. As you drive through your neighborhood, you'll see typically a big fenced-in area with big lines, conductors, switches, transformers. And then to our homes, so traditionally it is also an overhead line with a pole mount transformer, and that's what's shown over on the right. But more and more, our grid is becoming invisible to us because it's underground in our neighborhood, and you don't see the lines in the backyard anymore. There's a green box at the corner somewhere in your neighborhood, and all of that electricity is transmitted underground. So this is our traditional electric power system, and again, power flows left to right, downstream in this diagram. We also have money flowing the other way. So we are used to paying our local utility, and they purchase power because of deregulation enacted in the United States from generators that bid. In much of the United States, it is an active market where generators bid into the market. So the generators with the lowest cost are the ones chosen to supply the power. So as you need more and more power, you start using more and more expensive generators. And then the third layer of this is the regulation. So there is, especially in Texas, you see deregulation down at the residential level, but for most of the United States, and it is a regulated monopoly. So your utility company is allowed to operate as a monopoly. This is quite unusual in our market-driven system. But in exchange for that, they agree to be regulated. So at the federal level, it is the Federal Energy Regulatory Commission, FERC, that oversees. And then at the state level, there are public utility commissions. They go by slightly different names in different areas. But these are the entities that oversee the operation of your utility. So we have a technical, financial, and social system that all of that has to work together to bring affordable, reliable power to us. This is a typical load profile. So around 4 a.m. is when we have the lowest load per day. People are sleeping, machines are off. And then our biggest challenge within the grid is that early evening, late afternoon, when you hit your peak load. So this is the time when you have your most generators running. So if you have a generator down in the system, it's higher stress than earlier in the day. So that peak load is a very important aspect of the load profile for our system. Another very important aspect of the electric grid is that the load and generation has to be matched instantaneously. When you flip on a light switch, or if a big customer comes online that's an industrial customer, you can't wait for 5 seconds, 1 minute for a generator to come online. The electric grid, the way it is operated, at that instant, you have to have electricity provided to provide that load. And one of the reasons is we have very little storage within the electric power system. So it's only at about 2%. And most of that is pumped hydro storage, water being pumped upstream or uphill when there is light load, and then come downhill later in the day. So this instantaneous load and generation matching we'll come back to again. And this is a visual, as I had tried to describe in words. At any point during the day, you have to have generation stacked up. So as the load increases, you bring more and more generators online. And you start with your base load. Our nuclear generators are cost efficient, but they're not easy to adjust to load. And so when you hit those peak loads, you want more responsive generators to come online. So this is important aspects of our traditional power system. So now I'd like to talk about grid modernization. Some of you might have heard the term smart grid. Mostly now we refer to that as grid modernization. So the Department of Energy set up a grid modernization initiative some years ago. And they came up with this chart that describes the 6 main characteristics of a modernized grid. That it should be resilient, secure, affordable, flexible, sustainable, and reliable. And in the interest of time, with only about 40 minutes this evening, we will focus on the 3 highlighted in yellow. Resiliency. How do we keep the lights on, especially after a storm event or other disrupting event? How do we reduce our environmental impact with our generation? And finally, how do we keep costs reasonable for consumers? So those are the three aspects that we'll talk through. Resilience, defined as the ability to prepare for and adapt to changing conditions and withstand and recover rapidly from disruptions. Hurricane Sandy that hit the East Coast in October 2012 was a seminal moment for the utility industry. 8 million people were without power, some of them for weeks. And that inability to restore power in a timely fashion was a real wake-up call and sent many public utility commissions who regulate what the utility should be able to provide, and utilities who need to provide a service to their consumers back to the drawing board to think about how can we have a more resilient power system. And on so many of these, there are so many aspects that I could discuss, so you will probably get to the end of this talk and wonder, why didn't she talk about this? Because it's so important. And I simply had to pick some topics. So microgrids and self-healing systems are the two topics that I'd like to discuss here around resilience and how we are aiming to build more resilience into our system. So microgrid, as the name implies, is a small grid. So the ability to operate separately from the larger grid. So in this diagram, if you look at the top, the distribution substation, those little yellow, and sorry, I do not have a pointer, but the little yellow squares are switches. So if you open that switch, everything downstream of this distribution substation, if it was set up as a microgrid, would be able to supply its own loads locally. And you can have different scales of microgrids. So you could have a single customer microgrid. Very often an industry that is very sensitive to power disruptions will take on the cost and effort of implementing technologies so that they can be self-sufficient even when the larger grid is down. And there are several types of microgrids, several types of customers. I'm highlighting just a few here. The top left I chose as an example of a military microgrid. Many of the military bases within the United States are being upgraded so that they can operate as microgrids because the military has recognized that that is a risk to them, that they want to operate the base even if the larger grid loses power. Top right, this is a really ambitious project of New Jersey Transit, and this is very much an outcome of Hurricane Sandy. Because New Jersey Transit, because the trains are mostly electric, especially for rural trains, could not move people when the grid was down. So they are in the process of making sure that they can supply for themselves power when the larger grid is out. The bottom two pictures are some examples of community microgrids. There are also communities who say, we want more resilience within our community. Borrego Springs in California already has some microgrid capability for part of the town, and Potsdam is a proposed community microgrid. I do want to focus on this a little bit because for community microgrids, you do not typically carry all of the load within the community. You pick your critical elements, your fire station, your police station, your hospital, and also in hot areas, you might designate a school or a library as a cool zone that people can go to. So the community, you all gain, but you still might lose power at your house. So this becomes very challenging on how to recover those costs justly. Should all of the members of the utility, members or customers, pay for that capability? And I'm reminded here of St. Augustine saying charity is no substitute for justice withheld. And people are doing their best in thinking through what is the best way to provide these technologies and spread the cost in a just way. So that was microgrids. Going back to the larger grid, I want to talk about self-healing systems. This is a diagram that shows just a hypothetical network. Each of the houses here represent hundreds of houses, so these are communities. So we'll start with the system, and the boxes I've added here show that some of those communities, their power is supplied by substation 1, others by substation 2, others by substation 3. And then we want to consider what happens if you have a fault. So right in the center there, we have a faulted section. The first thing that happens is that your local protection will act. So we have circuit breakers throughout the grid that will open if they sense a fault current. So now you have a situation with 4 communities that are out of power because of that fault. And this is where new technology comes into play. Distribution management systems. These are software systems that utilities are starting to deploy. I would say maybe 30% of residential customers within the United States are served by a utility that has a distribution management system. So it's just really starting to be used to have a software system that takes feedback, real-time feedback from the field, and use that to locate the fault. So it runs algorithms to locate the fault, make sure that fault is isolated, and then restore service. So here you can see substation 2 is picking up one of those communities, substation 3 is picking up another community. So this is intelligence that is being added to the grid to automatically restore power after faults. And more you will be served by a utility that has this type of technology. And then I'll talk about energy efficient buildings, electrification of transportation, and variable distributed generation as part of this focus on a more sustainable grid. So zero net energy buildings combine energy efficiency and renewable energy generation to consume only as much energy as can be produced on site through renewable resources over a specified time period. Long definition, but typically that specified time period is 1 year. So with these buildings, it's not a matter of moment to moment having your renewable generation supply your load, but if you look at all the energy over a year that's generated on site, as long as that is equal or greater to the total energy used by the building, it's considered a zero net energy building. So it's fantastic, using less energy overall and powering more of your loads from renewable sources. But I do want to talk about what that does to the grid. So if you look at a typical home, again, here you see a bit of a morning peak when people get up, turn on the coffee machine, and then the evening peak when people come home. So if you build an energy efficient home, you simply use less energy for whatever you did before. So you reduce the base load, and then you add PV. So your net load now for a zero net energy home, that load profile looks very different from where we started. And a couple of important aspects there is that you now have power flow from the building to the grid. And where we started earlier with your power flow from left to right, from central generation station down to the load, that's what the grid was designed for. But now we're introducing a load that can produce power, and power flow goes the opposite direction. And the other thing that this introduces is this significant ramp, because right as you hit your peak in the evening is also the time when you lose your PV generation. So this makes it harder to get all of those generators online to make sure that you're matching generation with load every second. And this is sometimes referred to as the duck curve, kind of neck and head of the duck, and in Australia it's called the emu curve. And equally challenging in both places. Australia actually has a magnificent rooftop PV penetration. And this is not just theoretical. This is data from one of the buildings at NREL that has a significant amount of PV installed. So that thick black line shows the reverse power flow. So if it's positive, we're drawing power from the grid, negative, pushing power back into the grid. And you'll also see the big swings, the variability, which is another topic we'll come to. So this reverse power flow has some challenges. The two main ones are protection. Those devices, when we talked about self-healing system, your local protection that acts, those devices were designed, their settings were set up expecting power to flow in a certain direction. So much work and thought is going into how do we adjust our protection settings and design new protection devices that is better able to deal with bidirectional power flow. The second aspect is voltage regulation, and I'll just give a brief description, but again, with power flow from left to right, your voltage drops as you move further down the line. But now if you have generation at the end of the line, you could actually have voltages that increase as you go down the line. So it becomes more difficult for the utility to manage your voltage. They're obligated to supply that at 120 volts plus minus a few percentage points. So again, a lot of work going into that, algorithms being built into those distribution management systems to aid with the voltage regulation aspects as well. And then moving on to electrification of transportation, this is some data just to give some perspective on hybrid electric vehicle sales. So this is Toyota Prius. It took about 15 years to get to 2% of sales within the United States. So growing, but still small. And similar data for plug-in electric vehicle sales, Nissan Leaf, Chevrolet Volt being examples of these models. So over 6 years, they've achieved 1% penetration, so actually somewhat faster than hybrid electric vehicles. But it still, at this point, is a small percentage of our small vehicle fleet. So one of the concerns for the grid with electric vehicles is what happens if a lot of people, especially a lot of people on the same transformer, buy an electric vehicle. So I have a drawing down here that shows a transformer. This has 4 houses. But let's say you have a house peak load with about 10 kilowatt and you put 5 houses on a transformer. It's typically 5 to 8 homes on a transformer in the United States. So you'd want your transformer to be rated at roughly 50 kilowatts. So if each of these homeowners bought a car that has a typical charging rate of 3 kilowatts, you'd be adding 15 kilowatts. So there is the potential for overloading the transformer. Now, if you analyze this somewhat more, this is the worst case. So it's a simple example. You have variations among homeowners' behavior, coming home, etc. But still, this is one of the concerns with electric vehicles. So solutions being worked on in this area includes what we call smart charging. So again, having software that schedules the charging of the electric vehicle so that everyone doesn't charge at the same time. It does require some consumer flexibility to be willing to give over that control to software that I'm going to plug in. I know that I will be charged by tomorrow morning, but it might not be right now when everyone is using a lot of appliances in their home. And we'll get back to this need for consumer flexibility later as well. So increased renewable generation. In the United States, this is data from 2015, but still fairly timely, and I like this way of showing it. So coal and natural gas, about 2/3 of our energy comes from coal and natural gas. Nuclear, about 20%. I was recently reading a book, and it was kind of an interesting statistic that nuclear is about 20% of our power generation, and about 20% of our load overall is refrigeration, which means that nuclear power stations turn plutonium into refrigeration. It's one way of thinking about it. And then renewable, 13%. And of that 13%, the majority of that, almost half, is hydro. So the large hydro power dams that were built. Wind, also a significant portion. And then PV is still small. So if you look at 5% of 13%, you're looking at around 1%. So the pie chart on the left is a chart of worldwide where the energy, where the electricity came from. So solar is only about 1% of that. The middle one shows capacity. So that number is larger for PV because you do not get power the entire day. So there's a higher percentage of PV capacity. But if you look at new capacity, so expanded capacity in 2015, so 20% of all new generation worldwide that was built in 2015 was solar. So it's kind of 1% and 20% at the same time. And that growth in solar is due mainly to two factors. One of them is renewable portfolio standards. And this is a chart that shows so not all states within the United States has a renewable portfolio standards. But of those that do, you can see a cluster there that many of them are around 30% in 2020, those kind of goals, Vermont and Hawaii being outliers to that. So renewable portfolio standards drive this. So this is again from the regulatory side. The regulatory commissions can tell the utilities operating within that state how they should operate and that they need to have this level of renewable penetration in order to do business in that state. The other one is costs. These are some pretty dramatic graphs. The top one showing solar costs coming down, from 1976 at $80 a watt to, close to a couple of dollars a watt right now. And then the installations have grown rapidly once you hit a certain low cost point, and very similar with wind. So just tremendous growth in the last 15 years in renewable energy. But what does that do to our grid? So if you look at the penetration of renewables, and here this is plotted as a percentage of annual energy that is delivered, and it's a log scale on the x-axis. So these are actual operating systems, so small Alaskan village operating at 80% renewable energy, and then you have larger systems, and sorry, these numbers should be next to each other, but 40 to 20% in Germany. The asterisk there denotes that these countries are still connected to a larger synchronous system. So in that country, it might be 42%, but they can still connect to the larger grid in continental Europe to help stabilize. And then overall in the continental US, we're at about 5%. NREL has modeled other systems at higher penetration, so they have shown the ability to operate successfully with these levels of renewable penetration. There's California Lanai, one of the Hawaiian islands. REF is a renewable electricity future, so that's actually for the entire US. They looked at a 50% renewable penetration, and then the western and eastern interconnects. The Department of Energy has set goals of 35% penetration of wind and 19% for PV. Remember, we're at 3% on capacity worldwide right now. So these are aggressive goals. And what these studies have shown is that it's relatively easy to get to 25% penetration. We have feeders running at that level, but it's much harder to achieve the 50% goal. So there is still much work going into how do you design the grid to operate with half of the energy coming from a renewable resource. Because renewable resources have variability and uncertainty. So a coal or a natural gas-fired plant, you request a certain power level at a certain time. So it is called dispatchable. PV and wind are not dispatchable. You are subject to the weather patterns of that time. So this is one example, the red showing the insolation, and you can see that late afternoon, cloud passing over. So tremendous changes in power output at the time. So the grid has to be able to absorb that, because when this PV drops, it has to bring another generator online to make up for that difference. So this is a challenge, one of the biggest challenges with operating the grid with high renewable penetration. And one of our best tools to combat that is better forecasting. If we can better forecast, then we can better schedule our conventional generation to make up that difference. And then the other challenge here is that generation no longer follows load. So we have for so long, and to the largest extent, we still have a system where whenever you want more load, whenever you turn something on, the generation is there to supply it. But as we go to very high penetration of renewable energy, you now can't schedule that generation anymore. And this is, I grant, a fairly extreme example, but it is a real example of load that duck curve. So morning, flattens out during the day, and then that evening peak. But wind tends to blow more in the evenings and nighttime. And usually it doesn't drop this much during the day, but just to make the point here, I picked a fairly strong example. So here you have almost all your wind energy produced at night, but you need to use it during the day. So how can we address this? One way is to shift that energy through energy storage. So if you can save some of that energy during the night when the wind is blowing and simply discharge it in the late afternoon, problem solved. Challenge with energy storage is cost. One of the big challenges, so prices are dropping. And recently a colleague at NREL told me they've done an analysis that has shown that it's possible that by 2030, battery energy storage system may be able to compete with natural gas peaker plants. These are some of the more expensive resources that you turn on when you have a high peak load. But that's pretty encouraging to be able to have that possible option in 15 years to use battery storage instead of building another natural gas plant. So today, this is the world's largest lithium-ion battery energy storage facility. 30 megawatt, 120 megawatt hours. This is able to power 20,000 customers for about 4 hours. San Diego Gas and Electric just commissioned this system within the last year, and we will start seeing more and more of these large systems come online. But still, remember, today we're at 2%. So energy storage will be part of the solution, but not all of it. So another approach to this is, can we reduce our load when we don't have that much generation? And this is typically referred to as demand response. And how this traditionally works is, over on the left, the utility issues a demand response event to your home, and then they typically add an extra switch on your air conditioner or water heater, are the two main devices that this would happen to. And when they need some help in reducing load, they will turn off your water heater or your air conditioner for a short amount of time. On a water heater, it is almost not noticeable because there's so much thermal storage. Air conditioner, they can do that for a few minutes at a time, but this is typically a problem on a really hot day when people really want their air conditioners to run. So utilities are quite reluctant to use these systems, but it is tremendously helpful if you have thousands of customers who are just willing to live with a 2 or 3 degree difference. You can reduce your peak load by just those few percentage points that the utility needs. Utilities typically give a rebate, and in Colorado it's about $40 a year. So if you're willing to take the chance that they might turn this on, you get a small rebate. So newer programs do not simply turn off your air conditioner or water heater, but it sends a signal to your smart thermostat. This is much better for consumers because that thermostat is smart enough, or its third-party cloud service is smart enough, that it will pre-cool your house. So it knows that your air conditioner will be turned off at 4 p.m. So it actually makes your house a little bit cooler between 3:30 and 4, and then you have more headroom. So these programs are becoming much more popular. In this case, many utilities will give a free smart thermostat, and others also will give you a rebate if you say, well, I have this smart thermostat, and you sign it up for the program. So again, we need consumer flexibility, but for that small amount of discomfort on consumers' part that is spread out, we gain the ability to absorb more renewables into our grid, because now we can reduce load when there's not that much generation. And we can also have lower cost because you avoid the utility having to turn on a more expensive generating station to serve that peak load. So I work in this area, and we are looking at something that's called price responsive demand. And this is a situation where the utility does not issue an event, but it issues an incentive for you to change your behavior. So it could issue a price signal. So it could communicate a signal saying your electricity would be more expensive between 4 and 6. So then you have the choice But as consumers, that would be very tough for a person to react to that. So we're looking at smart homes with a home energy management system that takes into account this price signal that's coming in, the weather forecast, and your preferences, and schedules your appliances to keep you comfortable. But if the utility is either going to penalize you by a higher cost or give you an incentive, it can automatically react to that. One concern with that is, what if you have thousands of these on a feeder? So on this utility feeder, if all of those little gray dots is a smart home and they're all programmed to take advantage of these price differentials, what then? Here's just one simulation result from my work where we simulated a feeder with about 500 homes, all reacting to the same price signal. Oh, yeah, it shows it better on your screen. So the darker pink vertical bar is the high cost, and then there are shoulder prices right next to it. The bottom line is the power consumed. The dotted orange line is without this, all these home energy management systems responding to price, and the red line is with. And at the top, there's the average temperature within the house. So the dotted blue line is what it would have been if no one responded to price, and dark blue if they did. So you can see what these systems do, as I mentioned, they pre-cool. So right before the price goes up, it brings your temperature down so that you cool at a lower cost. And then you can see towards the end of that high price time period, it lets the temperature drift up a little bit because it knows the price is going to drop, and then I can cool the house and keep people comfortable. But you can see on the power, if this happened to the grid at a very large scale, and today smart thermostats is only a few percentage points, so it's not today's problem. But in the future, it could result in higher peaks than what you had before, and also more variability. So we would not want a system where we have a single price signal and everyone responding to that. So research is looking at how can you have intelligence that can design those price signals so that the overall behavior would not cause a problem for the grid. Again, this brings challenges and questions of how do you do that justly and fairly. If my neighbor has a slightly different price than I do, in order to get a better grid behavior. So there's always this technical, financial, and social aspect to grid work. So the final topic then is affordability. We have in the developed world, some of the lowest electricity prices. And we'd like to keep it that way, to keep the economy humming along, and we can spend money on other things. So Xcel, so I live here in Colorado, and Xcel is our local utility, and they recently started putting in this little pie chart in my electricity bill, which is pretty helpful. So what it tells me is that of my total bill, 2/3 of that, 66%, I pay for my electricity. So the more electricity I use, the more I pay. So it's kind of a unit purchase. But then another third of my bill, I pay, that is cost for what I call home delivery, or I think they call it home delivery. So this is how much it costs to get that to my house. So it includes maintenance, if there are outages, the utility's operating budget, if they have to have people that maintain the grid, keep it running. And not only that, the utility has kind of like a mortgage to pay off. They built a natural gas power station 7 years ago for growing load, and they're still paying off the cost of that. The problem, though, is that even those home delivery charges are based on how much energy I use. So if I use less electricity, personally, then I would pay less to the utility. So now we get to a possible situation that has many utilities worried, and it goes by the kind of melodramatic name of the utility death spiral. But to explain this, I thought this was a very useful chart. So as people put solar PV, rooftop PV on, so it might be for environmental motivations, but more and more it actually makes economic sense to get panels on your roof. So now you use less electricity, so you pay less money to the utility. But the utility, so you've reduced their kind of their fuel costs to supply the electricity, but they still have to maintain it. They're still paying down their mortgage. So they have higher costs. So they have to increase their rates in order to regain that cost. But now it is fewer people that are paying higher costs. So for more people, it now makes economic sense to put rooftop PV on their roofs. So it could spiral down. So this is a concern. And it again goes back to this issue of how do you justly assign costs? People who have rooftop PV panels use less electricity, but they still use electricity at night. They still use electricity if there's any issue with their rooftop PV or a really cloudy day. How do you fairly assign those costs? And in some states, they have tried to add fees to utility bills. It has been approved in some states and not in others. So this is a very active debate going on. This is a shared infrastructure like our roads. How do we keep it healthy so that all of us can continue to use it? So we need to reform our rate structures and our utility business models, and this is no easy task. So that brings me to the end of this discussion. So we covered resilience, how do we keep our lights on, sustainability, and affordability to keep costs reasonable for consumers. And I'd like to leave you with 3 final thoughts. Every time you plug a device into an outlet, you are connecting to a marvelously complex machine, technically, financially, and socially. But we need to invest in modernizing the grid so we can continue to have access to affordable, reliable, and sustainable power. And finally, I'd like to encourage you, there are technologies available that allow you to take a small active part in allowing us to keep our costs under control and absorb more renewables into the grid. Thank you very much.
Well, I want to thank you again, Annabelle. That was a few years ago, and now we've had a series of significant changes. Time, as they say, does not stand still for anyone, and certainly not for power systems. And so I think if you would take a few minutes, we've got a full 10 or 15 minutes here that we can work with. I've asked Annabelle, and she's thought to update us just a bit on what has transpired since 2017, because there's some key questions that you raised there, and you said, well, we will see in the future. So the future is now. Annabelle, you want to update us?
Yes, thanks, John. I'm going to switch over here to some graphs to help me. And it's very interesting to listen to this presentation from 3 years ago. So much of it is still entirely appropriate. But on the renewable side, there has been quite tremendous developments that I just wanted to point out. So, when I spoke, we were, around here, 2017, at the start of a pretty significant decline in coal. So over the last 10 years, coal has declined, gas and renewables have increased, and nuclear and hydro have remained pretty steady. So 2020 was the first year since 1950 that renewables surpassed either nuclear and coal in energy generation in the US, which is just, an amazing change within the power system. The another way of looking at this is, in 2020, 20% of annual electricity was from renewable sources. So it was 13% when I spoke 4 years ago. So still, wind has increased, continued to increase. So, and this is also the first year that wind produced more energy than hydropower. So that's also a significant change here, that growth in wind, especially, you can see is tremendous over the last few years. And then the final one I wanted to show was on cost of renewables. They continue to fall. So utility scale wind and solar are the most cost competitive forms of new energy. So existing plants are still, cheaper to operate. But if you were to decide right now what to build for new generation sources, they're the most cost competitive. Wind costs have decreased 70% and solar costs 90% since 2009. And these current prices for wind and solar energy are rivaling existing nuclear and gas plants and are below coal plants. So just an update there on the renewable landscape that we are within. And from there, I'd be happy to take any questions from the audience.
Annabelle, I was thinking as you're talking, the old law of ecology, you cannot merely do one thing. It applies to renewables and to this entire grid system, is that we increase our reliability on renewables, and as that takes up a greater proportion, then other problems crop up that we didn't engineer for before. There's always something new and different, and it's clearly a moving target. So I really like your 3 points there, that we're looking at resilience, we're looking at sustainability and affordability. Resilience speaks to the common good. We all benefit from having this grid and having these systems that are reliable and work. The sustainability question is really coming to the forefront, not only for the grid itself, but also with carbon and carbon generation. And as we try and push down on to address climate change, it sets up some other dynamics for us in the system. We switch from coal, we switch to other things. And then finally, the affordability and justice emphasis. I think that's so important. Just to finish that thought is that a few years ago, I heard the president of Duke Power, this is the largest, I understand, the largest single generating company in the world. He said something like, if we were a country, we'd be like, I don't know, number 33 in terms of our economic impact in the world, which is pretty stunning. And he said, there are 3 moments in which my performance is judged. And I think of that as believers in our stewardship and our work together. He says, 1, every time someone switches a light switch, they judge my performance. Every quarter, my board reviews my performance. And he says, and across a lifetime, my grandchildren review my performance. So we're building this grid and we're doing these things, not just for the moment, but for the longer intergenerational concerns. So thank you for putting this in context. And Paul Arvison is number 1 in the queue. Paul, if you just unmute.
Yes, thank you for this. NREL is a wonderful place, and I've toured there, and I love the place. And I know that it's been providing a lot of information for people, but I have solar panels on my roof. I've had them since 2016, and they're fine. Everything is great. I got a purchase power agreement, so it didn't cost me a dime. And I would like to see more of my neighbors to get into solar. I don't know why they're not. It just seems to be so slow in my neighborhood. And when I talk to people about it, the very first question they usually ask is, what happens to my bill? What is the cost? Because I guess solar has come down in price so much, people are still pretty wary about the cost. And the problem is, it's very difficult to answer that question. We have many different competing suppliers that can come in now. Electricity is a strange resource because it goes at the speed of light all over the United States, and people can switch between a number of suppliers, and it's just dizzy to try to figure out how to answer that question. I'm wondering if NREL has some tools like the vendors use that I could use to answer that question for people more precisely based on our local conditions, and give them some rough estimate what would the most competitive mix be for them in their in a house of a certain size or whatever?
Thank you, Paul. That's a great question, Annabelle. Is there some kind of tool that the consumer can access, or are we a ways away from that yet?
So I honestly don't know, but I made a note and I will follow up on this and maybe just send the answer to you, John. I know we have tools, NREL has tools, solar PV watts is the one that you can estimate the generation. But I think that's a very appropriate question that you have to be able to then translate it to cost. As Paul said, it's very hard because it depends on your supplier, et cetera. But I will definitely follow up on that because it seems that would be a very appropriate tool. Yep.
Very good. Bill, I think you're the next in the queue. You have a question, I think, in the chat too about CSV.
Yeah, it's the same question. I'll stick to that one. There are lots of questions I could ask. But so I've been interested in CSV for some time now. I think it's U of A that's doing salt, heated salt or something like that, because it addresses not only large scale electric generation, but also the storage problem. And I wonder, I know also the Biden administration, because I've listened to a panel talk they had about that. They're trying to pursue that as well.
Very good, Bill. Thanks for that. Annabelle?
Unfortunately, it's not my particular area of expertise. I know that some of the challenges have been on water. So where you site these and the cooling requirements to manage that particular technology. But I'm sorry, I'm just not an expert on the generation side of it because it's not really a distributed resource. I just tend to focus more on the distributed system. So it's PV panels on roofs is more what impacts my day-to-day research work.
Annabelle, thanks for that. All of us focus on different things, so maybe we can say what CSV is because it's
so it's concentrated PV. So it's not a panel that you typically see on a roof, but it's a big plant. So it actually concentrates the beams, and then it typically melts salt, and then you can store that heat in the salt. Yeah.
Right. Well, that's very exciting. That was one of those early technologies I heard out, I think, in the Mojave Desert.
Yep. And I remember 20 some years ago taking a tour of NREL with Ken Turion, and they had a setup here at NREL long before I worked there. Yeah.
That's great. Fred Cannon is next in our list. Fred, do you have a question?
Yeah. So, Annabelle, I take it you're at NREL in Colorado, right?
Yes.
You're in Colorado. Yeah. So I designed the water storage tank that's just above you on South Table Mountain.
Oh, I go running up there all the time.
You're going right by it. If you see a little screen enclosure, that's it. Do you know Rob Farrington at NREL?
No, we're about 1,800 people, and I'm over in the power system area. So our campus kind of goes from the biorefinery. There's been tremendous work in the biorefinery space, and then the people who work on PV cells and their perovskites is very new technology that is very promising for PV. And then over in the furthest building is where we deal with the power system and EV integration and microgrids and fuel cells and all of that.
Okay, so my technical question is, solar makes power right where it's used, so there's no loss of efficiency through a huge grid, whereas remote power or nuclear or whatever, there's just a huge loss of energy through the grid. To what extent is that magnitude, and could you comment on that?
Yeah. So the overall loss in the grid, because energy is transmitted at such high voltages, so power roughly equal to voltage times current. So that's why they make the voltage so high, so that your current is really low for a certain power, and then your losses, very roughly, is I squared R. So it's the square of the current. So if you can make your current low by making your voltage high, you actually have very low losses in the system. And it's been a while since I looked at these numbers, but I believe we only lose between 2 and 4%. So it's not an incredibly high number. So, I mean, the system we have is just phenomenal, in what it has been able to achieve as a centralized system. So it's not a 10% difference. It's a few percentage points in terms of efficiency. But yes, I mean, there definitely is benefit in using power locally. It's just, rooftop PV isn't always there. And unfortunately, it's often not there at 7, 8 p.m. at night when we're cooking food and heating our house, if we have electric heat, etc.
Annabelle, thanks, Fred, for that question. Annabelle, to this, the question of the complexity of this grid, we're committed, and we have committed over decades to a particular way of generating power. So the question has come in is that this sounds optimistic. This, in the midst of a major transformation, one unlike we've ever seen before, at a point in which the grid is aging. So you have these sort of multiple things going on. So the question is, you sound optimistic. Are things getting better, fast enough? It feels like the challenges are rising. What's your sense of us keeping up?
So my sense is it's not fast enough. But I mean, all I can do and our colleagues in the industry can do is to try to accelerate it. But no, when I look at some of the climate change goals that are out there, I don't think it's truly fast enough. But like you said, there's been mammoth investments. And the pace, those graphs I showed where coal is dropping off and renewables are rising, that is an absolutely tremendous shift within our industry to have been able to make that transition over the last 10 years. But we have so much infrastructure, our transmission lines, our transformers, our protection equipment. It's a mammoth task to upgrade all of it. The Department of Energy, I think some of their newest goals are even more aggressive. For 2035 to be, clean energy generation is, I don't know that we'll get there, but in my mind, I think it is worth it for us to think about and focus on finding solutions to get us there, so that even if we don't completely make it, we're building the right things that set us up to make it at a later point. So, yes, I remain engaged in it's valuable and it's worth doing it, and we have to keep doing it. But in the very big picture, I don't know that it's enough.
Well, thank you. It's really kind of putting you on the spot, right? And no one single one of us is responsible for what's going on, but this is our collective challenge, certainly as a society, and it cuts right across. The interesting thing today, unlike 40 or 50 years ago, you talk about these as global challenges because it's not just isolated to one nation state, one state. It's not even to North America. These are international challenges, and the dynamics are quite remarkable. Yes. Carl Lynch has been waiting. Carl, you want to unmute and ask your question?
There was a popular, 20 years ago, the whole issue of geothermal energy production came up. And obviously there are not regions of the country that are like Iceland, but I'm just wondering if there's any reconsideration or thoughts of maybe doing something with geothermal as a source.
So there is still active work on geothermal, but I just quickly checked the chart I showed. The US were at 0.4% in 2020. So you're right, it's very small. And I think even NREL's work reflects that there's a small group that continues to work on it. my very limited understanding is that it is hard to make it economically viable. So there are very few sites where it's economically viable, but it's ongoing. It's just small.
Okay, thanks.
To that, Annabelle, I want to play off of that because I was in a geothermal area doing research as an ecologist on some of the nasty outputs that come from geothermal in terms of acidic drainage into streams and whatnot. So, but in thinking about that, the question really comes to space heating in a home. Do we need thousands and thousands of degrees C in order to get us at 20 degrees C in a house? That's a long standing question. And many people have said geothermal, just local geothermal. And the question here is beyond geothermal. It's the question of, we have this massive grid. We committed to the large scale. Are there possibilities of shrinking things down to local generation and local sources of both power and heating? Is there work in that area?
So again, not my area of expertise, but the one thing that I will point out is we're fairly, in the US, we're actually used to local heating. We have our own furnace in our basement, where if you go to European, especially Scandinavian countries, it's a centralized heating solution. And there are definitely economies of scale with going centralized. But there again, it becomes social. Because we're used to it. We have our own system, we set our own temperature versus being in a connected system where people's behavior influence each other. So it's not just a technical solution. So the social side of this, how to really move people to change behavior is going to be key. I think someone mentioned electric vehicles. I saw a very interesting article just recently where the gentleman's point was that SUVs, sport utility vehicles, have become so popular across the world. In China right now, the latest data was 2018 or so, 50% of new vehicle purchases were SUVs in China. Even in Europe, it's at 38%. So it's not just Americans anymore who drive these big vehicles. But his point was the growth in SUVs will offset 10 million electric vehicles. So it's not just bringing the technology out, but the social side of it across the world. Yeah.
Well, is it, Annabelle, we are approaching, the 1:10 hour, and I'm here in Mountain Time, and I know you have another call to take. And so we want to thank you for being with us. This is just the tip of the iceberg, to use that metaphor. We are just, we're just opening up some really important questions. And maybe through local chapters, I see Lynn Billman has been waiting, and maybe through a local chapter conversation, we can continue this, because this is a very important and fruitful area of conversation for members in the ESA. I want to thank you all for joining us today. And Annabelle, thank you. And let's all give our reactions and claps in the either visually, or you can hit the reaction button. And Annabelle, do you have anything final you want to say to us on this?
Oh, no, I'm so glad you joined. It's delightful to see people engaged in this. And John, if there's a way, if you can copy the pictures, the questions in the chat, then I can follow up later, and also on Paul's question on the cost tools, and I'll get those out to you.
Very good. Thank you so much. We'll ask Becky to copy those questions out and make them available to you. I want to thank you all for joining us today for this ASA Brown Bagger opportunity to reprise some of our most important talks of the past and have them updated. We'll be bringing you another talk with Dr. Erin Smith on her discipline of psychology. That'll be coming up next month. So look for that announcement that'll be coming out soon. And thank you all for joining us today.
Thank you. Goodbye.